Alright, so welcome everyone for a new video where we discuss mathematics and physics on the whiteboard. And here, this is what we are going to do. If you can see the title here, what we are going to discuss is a sort of algebraic structure, which I'm not going necessarily to go into super details, but this is an algebraic structure which allows one to do algebra with segments, parallelograms, cuboids, and things like that. Okay, and so that's what we are going to look at. And in particular, we are going. One of the reasons why we want to introduce this is because this is actually used quite a lot in physics as well, and in some very important areas of mathematics, where some magic formulas come out of nowhere and actually come from there. So that's what we are going to do today. Okay, so again, today what we are going to do is simply introduce the notion of exterior algebra, and then in further videos we are going to develop a little bit more aspects of it and how it is used in other fields of mathematics and physics. But here, I want simply to focus first on for example, looking at a vector that I'm simply going to denote A. I'm not going to put any specific kind of arrow on top or bar under it. I'm just saying this is A, this is a vector. And then here I'm going to describe the magnitude of A with these two bars framing A here. Okay, and the point is that basically this A is going to be the length of the segment A, right? Of the oriented segment. Okay, so that's kind of traditional. A vector is essentially an object that has a magnitude and a direction. So here you've got a direction that is characterized by it, and then the magnitude is going to be the length of that particular geometric object, which is this straight kind of segment. Okay, so that's kind of standard. This is something that you would have seen in high school, perhaps even like in some earlier stages of secondary school, and of course in linear algebra and so on. So you can add up vectors, you can multiply vectors by a real number, and so on and so forth. Okay, now what is less known is what happens when we actually have two vectors. And so in which case, let's say we've got let's say here we've got the vector A, and now I actually put another vector which I put here, and that I'm calling B. Okay, and the thing that is interesting is that this particular object, from it, as you know, you can basically construct a parallelogram from it. Okay, and so you can, and that's what the exterior algebra allows, you can create an object, an algebraic object that is called, that is denoted A wedge B. Okay, and this A wedge B characterizes the entirety of this parallelogram. Okay, so it's an object that you write with an algebraic operation, which is the wedge here. So this wedge is called the wedge product. It's called the wedge product. And sometimes, of course, it's called the exterior product as well. And so the idea is that basically when you take the wedge product of two segments, you actually get an actual surface. Okay, and the surface is characterized uniquely, at least if you want to interpret it in that particular fashion, as made up of these two vectors and then with the parallel version there. Okay, so this formula tells you I'm building a parallelogram that is made of the vector A and B. Okay, so that's what this AB stands for. And what is interesting is that if I want to look at the analogy here, I would like basically a wedge B. The magnitude of a wedge B has to be, if I want to be consistent with what I have here, it has to be the area of the parallelogram. Okay, that is made of the vectors A and B. Okay, so this is interesting because we can try to work out a property such that essentially if I take the wedge product of a vector and another vector which is collinear to it, okay, so that can be expressed as a simply a multiple of the initial vector, then I should get zero area. Okay, so that's kind of the point. We want a definition of that product that automatically is going to give you zero for that. And as it turns out, the way to do that is simply, really simply, to require that A wedge B is equal to minus B wedge A. Okay? And the reason why that's the case is because if you, so let's continue here. The reason why that's the case is because, and that's a sufficient condition for at least ensuring that the area of the parallelogram is going to be zero in this particular case. You're going to have, if you take the example, if you impose that particular definition, okay, that A wedge B is equal to minus B wedge A, then you're going to have that A wedge A is equal to minus A wedge A. Okay, and the only number which is, if you look at the magnitude, the only number which actually satisfies that is zero. Okay, zero is equal to minus zero, and so we automatically get that A wedge A is equal to zero, and that's true for any vector A that you would take. Okay, so that's kind of the idea. But with this particular structure, we can also see kind of what happens. So what we can do is do the following. So we are in 2D for now. So let's imagine that the vector A is equal to some A1 U1 plus A2 U2. Okay, and then we have B is equal to B1 U1 plus B2 U2. Okay, so then because it's a product, basically it maintains the property of so-called distributivity with respect to the addition here. So what I'm going to get is the following. I'm going to have A1 U1 plus A2 U2 and then wedge, and then I've got B1 U1 plus B2 U2. And U1 and U2 are some kind of unit vectors, or they can be whatever you want, some kind of reference vector you want to use here to describe A and B. Okay, so once you're there, you simply expand everything. So this is going to be equal to, so we are going to get A1 B1 and then U1 wedge U1 plus A1 B2 and then that's U1 wedge U2. Okay, and then below it we are going to get A2 B2 U2 wedge U2 and then plus A2 B1 U2 wedge U1. Okay, now keep in mind what we just wrote here. A wedge A is equal to 0, whatever A is. Okay, so what that means is that this particular object here is 0, and likewise this one here is equal to 0. And remember as well that u2 u1 is actually equal to minus u1 u2, okay, by definition. So in the end, what we end up with is the following. We are going to get a1 b2 minus a2 b1 and then u1 u2. Okay, so let's go back to this board in a minute. All right, okay, so we're back, and so I've just rewritten this formula here, and if you look actually at this particular expression, you can recognize that this is the determinant of a b, okay, of the vectors a of the matrix that is made of the components of the vectors a and b in the basis u1 and u2 times u1 wedge u2, okay? And then what you get is that the magnitude of a wedge b is equal to the determinant of ab, or the absolute value, because the determinant may be negative, you never know. So the absolute value of the determinant, and then times the u1, u2. So the magnitude of the elementary kind of parallelogram you're looking at, okay? So essentially what you see is that you start from some elementary parallelogram, and then you've got A, B that has a particular relationship to that original reference parallelogram, and the transformation when you want to calculate A wedge B is related to this determinant here. Now, one of the things that happen is that if you choose, so if u1 and u2 are chosen so as to be of length 1 and perpendicular, to each other, then the area that is made of basically the square with vector directions u1 and u2 is going to be directly 1, and so therefore you're going to get the traditional formula that the area of a parallelogram is equal to the determinant of the vectors that are making this parallelogram expressed in an orthonormal basis. Okay, so that's a classical result of linear algebra. Okay, so that's for the 2D case. One final thing that I need to say is because we can have a minus sign appearing, we can wonder about the actual meaning of that sign. And as it turns out, when you've got a surface, you can characterize this surface uniquely as well. I mean, not uniquely, but you can view this surface as being also associated to an orientation. And this orientation has to do with whether or not you want the normal to that surface to go outside of the board that way or to go inside of the board that way, okay? And usually this is represented by a circulation direction. So here you would, for example, create by convention a circulation direction which goes that way, so anti-clockwise, and corresponding to it, the normal is going to be the plus, if you will, direction is in that direction. So basically that's how that would work for the convention plus, where from A to B you've got this particular plus kind of direction going on. Okay, so basically that's what happens in 2D, but the reason why this is a very useful concept and notion, this wedge product, is because essentially you can extend it to higher dimensions. parallelotop. Right, okay, so now what we can do is actually see what happens when we are in 3D. So here, this is an attempt at basically looking at a parallelogram for the AB, okay? But then we also have a depth to it via the vector C. And as it turns out, this particular object is going to be characterized by the wedge product A, B, and then C. And basically that's it. Nothing more is needed. This is going to be fully characterized by that particular product. Okay, and of course, this is going to be a so-called oriented volume. So you need to imagine that as being, let's say, in a larger dimensional space so that you can characterize kind of orientations in there and so on. But basically, this is going to have some form of direction, which you can try to represent, but that wouldn't be that's a so-called isomorphism as corresponding to the different directions having to do with the basically the two A and B, and then you take for example B and C, so you're going to have a loop here as well, and then you've got A and C like so. Okay, so you're going to have directions associated to these loops you can create depending on taking the different pairs of vectors. But the bottom line is that A wedge B wedge C corresponds to this particular object. At least that's one of the possible, and in my opinion, the simplest interpretation of this particular object that is made out of these three vectors. And then, of course, the thing is that the A wedge B wedge C has to be equal to the volume of that that object. I'm not sure how it's called in 3D, but in general, this is a parallelotop. Parallelotop. I think probably like this. Um, and um, and so that basically that's it. Now, what happens is that if we apply the same formula that we have used before, we are going to get that this particular volume is equal to the determinant of A, B, and C when they are expressed in a basis U1, U2, U3, which is orthonormal. So what that means is that you're going to have an elementary, let's say, cube like this. Okay, and you've got here U1, U2, and U3. And basically what you say is that this actual object is a determinant of A, B, C, and then times that particular thing. Okay, so basically you can express all of this via this particular objects. Okay, but by the way, what you're going to find is a bit more. I mean, it's not more complicated than that because it's only depending on U1, U2, and U3, nothing more. But yeah, you're going to find that this is basically a skewed kind of cube, and that includes as well the directions and so on. Okay, because here you've got three directions anyway, and here you simply are going to have different magnitudes for these directions. Okay, so basically that's how that works. This could be expanded in principle in 4, 5, 6 dimensions, so you can define and conceive of basically parallelotopes that are like 5-dimensional and basically write what they are in this particular fashion by doing the exterior product. It does have always this property of so if I swap A and B, I should get a minus sign. If I swap B and C, I should get a minus sign. If I swap A and C, I should get a minus sign, and so on and so forth. Okay, so that's just the tools that I wanted to present to you today. And basically what we are going to do from here forth is basically try to use these particular tools in order to talk about integration, differentiation, fields, scalar and vector fields, and so on.